Rate law is the expression in which reaction rate is given in terms of molar concentration of reactants with terms raised to some experimental determined power. So, rate expression says the powers of concentration of reactants is determined experimentally. That's what the rate law says. I mean, we're not able to determine theoretically. Let's take a general chemical reaction. Reactants A and B with coefficients small a and b, and product C and D with coefficients small c and d are expressions in general reaction. So what is the rate expression? That is, we having a reaction rate constant here, which is a constant for the same reaction at a particular temperature. Then our concentrations of reactants, which are represented in square brackets, are raised to power x and y, which are experimentally determined numbers. So powers of reaction rate expressions are determined experimentally. These can be integral numbers or fractional numbers. Both are possible, but remember the point. The power of reaction rate expressions are determined experimentally. And if we sum the powers of concentration of reactants in the rate law expression, that's called order of that chemical reaction. Let's say take a simple example. We having a reaction of nitric oxide with oxygen to give us nitrogen dioxide. These two atoms are reacting. First stage, we have doubled the nitric oxide's concentration from the nitric acid tank. We supplied it. This concentration is doubled. What we saw, the rate of reaction increases by a factor of 4, which means rate depends upon the square power of concentration of nitric oxide. That's why the concentration has gone up to 4 times. So the reaction rate has gone up by 4 times. In another experiment, we kept the nitric oxide concentration constant and oxygen concentration was doubled. The supply of oxygen was doubled. What we saw, the rate for reaction get doubled again, which means we have doubled the oxygen supply or oxygen concentration in a reaction mixture, and the reaction rate for this has gone 2 times. Means it is depend upon a single power. So rate law expression will be reaction rate constant, as we know, and concentration of nitric or nitric oxide raised to power 2, oxygen raised to power 1, because it's only doubled, so it will depend on 1, and order of reaction will be 2 plus 1, 3. So order of reaction can be fractional as well, because rate law expressions powers of individual concentrations are determined experimentally. We discussed about it. Sum of powers of concentration of reactants in rate law expression is called order of reaction. Zero order reaction is where the concentration part is totally independent. Our reaction rate doesn't depend upon the concentration of reactants. So we have raised them to power 0. and reaction units of the rate constant will be mole per liter per second, because our reaction rate we know moles per liter, that's a concentration, and per second, and division by our concentration side equal to reaction rate constant. That's why its unit will be same as rate of reaction. A first order reaction, where it's depending, here is the reaction rate, and then that is divided by total concentration of reactants. That is first order reaction, it will be 1, and so the sides are cancelled out, we are getting a per second. So reaction rate constant for first order reaction will be per second. Second order reaction, mole per liter per second, will be mole per liter second, that divided by it, so it will be as its inverse, so per mole liter per second for second order. Same thing goes to third order, it will be mole per second square liter square per second. That's how the reaction orders can go further as well, third order, fourth order, and all that. First, zero order reaction, which having a reaction constant mole per liter per second. Zero order reaction means rate of reaction is proportional to the zero power of the concentration of reactants, that is independent of the initial concentration of reactants. Example is decomposition of ammonia into nitrogen and hydrogen. Reaction rate will be reaction rate constant, ammonia raised to power 0. It means it doesn't matter what is the concentration of ammonia, this decomposition reaction will be of independent of ammonia concentration. Decomposition of hydrogen iodide into iodine and hydrogen. Nitrous oxide decomposition into nitrogen and oxygen. It's again a zero order reaction. Now, to explain it mathematically, let's say is a change in concentration of our reactants, then dA by dt is equal to K. The negative sign, as we know, symbolizes reduction in the concentration of reactants. By taking the integral, we get concentration from AT to A0, because initial concentration was A0 at time t0, at time t it was AT, so it will be AT minus A0 and minus equal to minus KT, and in such a case, that's what is our expression for zero order reaction. If you see at a time, T0, this will be 0 and concentration will be equal to A0. So the intercepts of reaction gives us a initial concentration, and slope of it gives us a reaction rate constant. Zero order reaction constant will be K. Now half-life of a zero order reaction will be at time equal to T half, mean at a half time when concentration of AT will be reduced to half of initial concentration, substituting the value AT equal to A0 half and T equal to T half, mean at a half-life reaction time the concentration will be reduced to half. So what we will get, KT equal to A0 by 2. That's the expression for half-life time, first order reaction, reaction constant will be per second. The examples are hydrolysis of ester, thermal decomposition of nitrous pentoxide, hydrolysis of hydrogen peroxide, mean it will goes into decomposed into water and oxygen, decomposition of calcium carbide. So we are getting calcium carbonate into calcium oxide and carbon dioxide. Now let's try to understand it mathematically. dA by dt equal to minus K1. A is a concentration of reactants. And here, if you remember, it's a semi-log graph. Concentration is in log natural and T time is in natural time. So here, in first order reaction, concentration will be depending on the first power of reactants. Let's integrate it from A0 initial concentration to A and 0 time to T. We are getting a log natural A0 to A minus K1T 0 to T. So log natural A minus log natural A0 is equal to minus K1T. We rearrange it to get a log natural A equal to log natural A0 minus K1T, or we get this expression. We will take this one. This is a log natural A divided by A0. So log natural A divided by A0 equal to minus K1T. Taking log natural to other side exponential, that is exponential minus K1T, and A divided by A0, A0 goes here. This is another expression for first order chemical reaction. Expressing it 2.303 log natural A0 by AT equal to K1T, because earlier it was, you see in the previous reaction what it was here A by A0 and the negative sign is here. Here A0 goes up, so we are getting a A0 by AT, and negative signs, so change in that. Half-life of first order reaction, as we know, at a half-life time, concentration will be reduced to half of initial value. It means initial concentration is here 100%. It will fall to 50% at first half-life time. At first half-life time, we substitute the value here ET is equal to E0 divided by 2. What we'll get? That's it. At 50% concentration at first half-life time, this is 2.303 log 2. Substituting the value for log 2, we'll get 0.693 divided by K1 equal to half lifetime of first order chemical reaction. This is a simple expression you can remember, useful. Now in next half lifetime, the concentration will be reduced further 50% to 25% and 25% to 12.5%, 12.5% further into 6.25%. This is how the concentration will keep on reducing in every half lifetime. Second order reaction. What is the example of second order reaction? Here, decomposition of nitrogen dioxide into nitric oxide and oxygen. That is, reaction is mole per liter per second divided by moles per liter into square. So this reaction rate constant will be per mole liter per second. That's what it is. we integrate it, what we are going to get is we get it minus 1 a by 80 from E naught to E naught, and time is from t to 0, that's the initial time. Further, remember here is a negative sign because of the concentration of reactants is reducing, we discussed earlier. So after rearranging it, our reaction rate expression will be 1 by A naught minus 1 by Et is equal to minus K2T. That is expression. Further, at a half-life time, we know A2 will be A naught by 2. Substituting the values, what we will get is 1 by A naught is equal to K2 T half. So T half will be 1 by A naught K2. That's the reaction rate constant. These are certain expressions that will be helpful to find the half-life times. You can remember it. For first order reaction, it was 0.693 divided by reaction rate constant. So half time, we will remember always, is inversely proportional to reaction rate constant, and first order reaction rate was independent of concentration, and in zero order it was A naught by 2K. So to keep that small things in your mind. Here, if we plot it, it will be the intercepts here will give us the inverse of initial concentration. So again, slope will be reaction rate constant.